So this is lecture 5, and this lecture will be on transformation or function of random variable. So this is on function of random variable. So it is also called transformation of random variable. So let x be a random variable with some distribution function said f. It may be discrete, it may be continuous, whatever, and g is a function from R to R. Is a function from R to some, say g equal to, say gx equal to x square, or maybe sin x, whatever. This is the function from R to R. Then the question, if I take y equal to gx, and then is this y is a random variable? Is the question is a y is a random variable? So answer is yes, if g's have some property. So g have some property. So if g is Borel measurable function, then this y is the theorem is this. So let x random variable defined on this probability space, this omega, shift and p, and g is a Borel measurable function. R to R is a Borel measurable function. Borel measurable function. Measurable function. So it is a Borel measurable function. Then gx is also an random variable. So this is also a random variable. So what is a proof? Proof is just trivial. So we have to show that gx is random variable. So to show, so where gx is defined from, remember that gx is defined on that script, that omega to r. So because your x is from omega to r, and your g is from this r to r, that means your this compose function, that gx, g compose x, that is from omega to r. So what do you have to show? To show that we have to show that gx less than or equal to y, that set must belongs to the script S. That must be an event. So every Borel set, that inverse image must be Borel, that in event, that in event space. So this is we write notationally a G inverse. So for G is a GX inverse of Y, GX whole inverse of Y. So this is a notation. So what is this? This is actually X belongs to that random variable belongs to that G inverse of minus infinity to Y, close interval, because less than or equal to. So there should be one more bracket. So this set, and we know what is this set. This is nothing but omega belongs to omega script capital omega, so that x omega is actually belongs to G inverse of that minus infinity to Y. This set. Now is this set script S? Now, since G is a Borel measurable, G inverse of that set, so this is a Borel set, this interval is a Borel set, so this is a Borel set. So this belongs to the Borel sigma algebra, and since this belongs to the Borel sigma algebra and x is a random variable, therefore this implies this set is actually this collection, this set is actually in script S for all y belongs to real number. So since G is Borel measurable and x is again a measurable function, randomly is a measurable function. So actually composition of two measurable function is again measurable function. That is a more general result true. So random variable is a measurable function, and G is a Borel measurable function. So is also measurable function. So that's why the compose G compose X is a Borel is a measurable function. So it's a random variable. So it's easy. Now then there is one more theorem. So this important theorem is this. So G is more representable, and now this is the other way. The converse is this. We have this also the converse like that. If X is a random variable, that conversely we can write conversely. Conversely, X is a random variable. X is a random variable. And X is a random variable, and that Y is Gx. Not the converse. It's actually moreover with the extra thing. So moreover, X is a random variable, and that Y is that Y, which is Gx, is a random variable with what is a distribution function. The distribution of random variable is like that. So distribution of distribution function of that Y is just probability of Y less than or equal to Y. This is nothing but probability of X belongs to the G inverse of that set. That set. So probability of this set. So this is a distribution of Y. So let's quick look on an example. So X is just a random variable with distribution function say capital F, and take some mod X. One function is mod X. Say another function is say Ax plus B. Say another function is x to the power k. There are three functions. And say another function is say mod x whole to the power alpha. So what is AB? AB are all real, and all AB, alpha, k are all real. Is are all real, and not only that, so is are all real, and A is not equal to 1. A not equal to 0. Is A belongs to the real number. B is any real number. Your k is an integer. K is an non-negative integer. And alpha is some positive real number. Then this all four types are random variables. This all four are the random variables. So how do you prove that this all four are random variables? So to prove it, we have to define one function. It's called x plus. X plus is a one random variable is x if x when x is greater than or equal to 0, and 0 when x less than 0. And similarly, we define x minus, which is x when x less than or equal to 0, and 0 if x greater than 0. Then what happened? Then x plus and x minus both are also random variable. It is clear because it is just x with some restriction, and if you take the inverse image of that set inverse, this is actually take the Borel set, that intersection of the set of positive non-negative real numbers, and then so since it is a Borel set of all non-negative real numbers, and Borel set intersection with another Borel set is Borel, so inverse image of this is a random, also random variable. Now what is the mod x? Mod x is nothing but is x plus minus x minus. So this is mod x. And this is random variable. So sum of two random variables is random variable. And what is the distribution of that? What is the distribution of that? So it's a random variable, and distribution of that mod x, so it's less than or equal to y, that distribution function is just, you have to take the probability of that set, you have to take the probability of this set. So mod x less than or equal to y, or you have to take the positive y, and for negative y it is just 0. For negative y mod, probability of mod x equal to y less than or equal to y is 0. So this, and what is this? This is nothing but probability of x less than or equal to y minus probability of x strictly less than minus y. Now what is this? This is the distribution function at y minus distribution function at minus y plus one more extra thing, the probability of x equal to minus y. So this is the distribution function, and now similarly you can find the probability of that linear function of that distribution function y, and that x, this x plus b. What is this? Since it is linear, it is just ax less than or equal to y minus b. And what will be that then x less than or equal to what? Now if a is positive, then it is x less than or equal to y minus b. So there are two cases. So if now if a is positive, we have this. If a positive, and if a negative, then what happens? Then this is probability of x greater than or equal to y minus b. So we can find that probability. Now what is the probability of what is the distribution function of x plus? The distribution function of x plus is this. So this will be 0 if x or y less than equal to less than 0. It will be if y equal to 0, then this is just probability of x less than equal to 0. And that if y equal to 0, say, so it is x plus is less than equal to 0, that means your x is less than equal to 0. If x is negative, then this x plus is 0. But x plus cannot be less than equal to some minus number quantity. So, now if x is y is positive, then what happens? Then this is actually x less than equal to what? It is y. So it is less than equal to y. So for x negative, this part will be 0, and that for positive part is less than equal to y, because y is positive now. Similarly, for x minus, this is will be 1 if x is positive, and this is x less than or equal to y Actually, we can just put together these two things, and we can write that if y greater than equal to 0. So, and this is less than, if less than greater than equal to 0, it is 1, and strictly less than 0, then it is x less than y. Now, let x be a random variable of discrete type, and say A is a countable set. Be the countable set such that the probability of x in A, this is 1, that countable set. We know that is a countable set, and that probability of x equal to x is positive. We take the only positive part, and that is at most countable, maybe finite, for x belongs to A. That may be finite, countable, or maybe it may be finite actually. If it is a finite random variable, it may be countable, or it may be finite, or finite. Since we take the all positive part only, the positive probability part only. Now let that y is equal to gx, and this is this g be a one-to-one function. That is a one-to-one function. Let g be a one-to-one function. So we, and one-to-one mapping from A to some other set B. Now, then what is about the inverse image? So, what is it then? With the inverse image exists, then G inverse exists. It is one to one. So, this exists. G inverse is exist. Inverse function exists. Now, how do you find that probability of y equal to y for the discrete case? It is just probability of gx is equal to y, and that is probability of x is equal to g inverse y. So here it is a only inverse function exists. So g inverse y is a single value, and single value is a single real number. But if g is a many-to-one function, is not injective, then this set g inverse y is not a single valued. Then inverse it does not exist, but we can take the set inverse of that. And obviously, the probability of y equal to y is must be 0 for when y does not belongs to B. So this is the probability mass function of that transform variable. So there are several example maybe like that. One example is x gx equal to x square, say. So take one more example that x is uniform random variable. So x is uniform on -1 to 1, say. So -1 to 1. So it is a discrete, now it is a continuous case. So what is the PDF of that? So PDF is if f, say fx is what? Fx is half for this set, and it is 0 otherwise. So otherwise, so we sometimes we write in the indicator function notation is like that, half into indicator function of this set. So that is a much easier and elegant way to write this thing, this uniform random variable. So indicator function of x into half. So if x is in this interval, then it is half, and if not interval, then it is 0. Indicator function says that. Now what about that probability of x plus less than or equal to y? Now we can easily check that if y is negative, then it's obviously it is 0. If y is 0, then it is half. Just less than or equal to 0 is half. If 1 it is greater than 1, then it is 1, and obviously between 0 and 1 it is just half plus y by 2. You can easily check that probability. So this is a jump at y equal to 0. So this is a jump. So what will be the look like? That distribution function looks like that. So up to 0 it is 0. At 0 it is half. Then goes to straight, and half it is 1. Sorry, at 1 it is 1, not half. So it is slightly flatter. So at 1 it is 1, and then goes straight. So clearly this is then this x plus is neither discrete, so it is a jump, so it can't be continuous, neither discrete nor continuous. It can be continuous. It's not a discrete because it's not a constant in other. It's not a piecewise step function. So next theorem is most important theorem in this transformation thing. So the theorem is this: let x be a random variable of the continuous type, say continuous type. Now with PDF, that PDF is say f. Now let G is a R to R, the differentiable function. It is a differentiable function. Differentiable function, and has the extra property g dash x is greater than 0 for all x. That means it's a monotonically increasing function, or g dash x is less than 0. It's a monotonically increasing function or monotonically decreasing function. So it's a monotone function, differentiable function, and g is monotone function. So either monotonically increasing or decreasing. So it may be, it is actually monotonically, strictly monotonically increasing or strictly monotone. So it is strictly monotone. So it is strictly monotone. Strictly monotone function. It may be decreasing, maybe increasing. Since the derivative is positive and negative, it is either positive or either negative. So it is not that somewhere it is positive, somewhere it is negative. Either it is all positive or all negative. Then the result is that random variable y, which is gx, is also, this is also a random variable of continuous type. This is also continuous type. And with this PDF, what is a PDF of that f and that y is PDF h, where h is given like that, hy is equal to that f of g inverse y. Remember that g inverse exists because monotone function is 1 to 1. So monotone function is 1 to 1. So that means g inverse exists in the suitable range. So we know that every monotone function is 1 to 1. every monotone differentiable continuous function. So it is a inverse also continuous. So this is a continuous, and then you have to multiply it by a quantity which is called the Jacobian of this. For one variable, it is ddy of G inverse y. That G inverse ddy of G inverse y, and that must be in. It's not in the whole real number, because that G may not be surjective. So once this is not surjective, G inverse not exist for the whole R in the whole R. So it is G inverse exists for the some suitable domain. The domain is in that from alpha to beta, and obviously 0 otherwise. And where it is that PDF is that what will be the alpha and beta? Alpha is nothing but the minimum of the two number g of minus infinity and g of plus infinity is the minimum. We know that for a continuous function, that range, the whole range is actually the minimum to maximum, and the maximum is that beta is the maximum of g of minus infinity and g of plus infinity. The proof is straightforward. So g is differentiable since it's differential for all x. And let g dash is positive for all x. First let the case where it is positive, strictly in place for all x. Now then what? Then g is, since it is differential, so it is continuous. G is continuous. Differential function is continuous, and it is strictly increasing, strictly monotonically increasing function, SMI. And then we know that the limit exists, maybe infinite, that alpha beta may be infinite, so infinite limit, but that limit alpha beta exists. So therefore alpha beta exists in the extended real number system. In extended real number system. Extended real number system. So that may be infinity or minus infinity. That alpha beta exists. And this inverse function is also exist. We know that G inverse exists. So it is continuous and strictly monotone increasing or strictly monotone decreasing in monotone function. Strictly monotone function actually. Monotone function may not inverse exist, but strictly monotone is injective. So G inverse exists in suitable range, that in alpha beta, and strictly monotonically increasing. The inverse is also strictly monotonically increasing, we know, in alpha range of alpha beta. So in that suitable range of alpha beta, that alpha sorry, it's not infinity, it's alpha. And if alpha and beta are, if alpha is the minus infinity and beta is infinity, then we just take the open interval. We can't take the closed thing. So if alpha beta finite, alpha beta finite, or we can just minus infinity to beta, if beta finite, or alpha to that alpha to plus infinity if alpha finite, or if both infinite or that minus infinity to infinity, if both are infinite. Okay, we just take just open interval, say. So then we know this is strictly infinity, so therefore this is differentiable on that my alpha to beta open. So open interval is differentiable. And what is the distribution function of y, that gx? The distribution function of y Now we have to take for that open interval is given by that probability of y less than or equal to y is just probability of x less than or equal to g inverse y, that you see. Now how do you get the density function? So you have to take the derivative, so you have to differentiate this dy of that, you have to differentiate. So once you take the if you take the differentiation of if you differentiate that quantity, then it will get the PDF of this is the PDF of that is hy, that is a PDF of this. Now how do you differentiate the right hand side? So therefore what is hy? You have to right hand side, you have to differentiate is just the chain rule, you have to use a chain rule. So it is just f of g inverse y, and you have to take the chain rule of that. So dy of g that. So you have to take there's a chain rule. Using chain rule, this. So we have this. So we just put a mod. Obviously, this is it a positive. We can. It is same as that mod value. Since this is positive, is you can put mod, or we can't just drop the mod thing. Since it's positive, remember that the derivative is positive. Now similarly, if derivative of g is negative, that is strictly decreasing function. G is strictly monotonically strictly decreasing function. Then all these things are true. That differentiability, that inverse existence, all is true. The only difference is this: the probability of y less than or equal to y is then probability of x. Now it is greater than or equal to g inverse y. Just sign changed. That inequality changed. And what is this? This is a 1 minus probability of x less than or equal to g inverse y. Remember that is a continuous type. So since the probability of x equal to a single point, it is 0. Remember that single point is 0. So again, if you take the differentiation, that if you differentiate this thing, take the derivative of this, the left hand side is hy and the right hand side is just minus. Same thing, f of g inverse y, and derivative of that by the chain rule, derivative of g inverse y. Now we can put the mod value of that. So it is just, since it is negative, we take the minus sign inside and put the mod value. So this is by mod dy of g inverse y. So this completes the proof in the both case. It's strictly increasing or strictly decreasing. So this is a very important thing. So we first give an example of that. So take the standard normal distribution, say. Take x follows normal distribution 0, 1. So what is the PDF of that? So PDF of this is, say, f, and what is f? Fx is actually 1 by root 2 pi, sorry, no sigma is there, root 2 pi e to the power minus x square by 2, and this for all x in R. Now if you take a g is a function of x square, the square function, so y is x square. Okay, it is now not monotonically increasing or decreasing. So what will do in this case if it is not monotonically increasing or decreasing? So okay, well, we give this example later. First we give an example of monotonically increasing or decreasing function. Take that example first. So let X has a density. The PDF of X is a random variable, and PDF of X is, say, F, such that Fx is 1 in 0, 1. So it is uniform rectangular distribution and 0 otherwise. So we just write Fx in indicator form. So it is indicator random variable of 0 to 1 as the indicator function of 0 to 1. Now take g as e to the power x. Gx is your e to the power x, the exponential function. So y is e to the power x. Now what is x? So it is strictly monotonically increasing. So g is strictly monotonically increasing function. So what is x? It is just log of y. Now remember that y must be positive to define that log. Now what is your that density function PDF of y? So say y is, say, PDF of y is, say, h. So what is hy? So it is just what? It is what we get. This is f of g inverse y. So g inverse y is so what is g inverse y? It is log x. Sorry, log y. Now f of g inverse y into the mod value of the derivative, mod value of so this is mod value of d dy of g inverse y. Now what is f? F is either 1 or 0. So when this is 1, g inverse y is 1 when this is 1. So if that x is lies between 0 and 1, then it is 1. So g inverse y, so g inverse y is log y, and this is, we know that log y, that derivative of log y is 1 by y. So this is that, and that f of log y is what? It is either 1 or 0. So it is 1 when it is 1, when this log y is between 0 to 1. So otherwise it is 0. So and it is otherwise 0. So this is otherwise 0. So what? So what is hx? Hx is now log y is between 0 to 1. What is the meaning of that? That means y is in from 1 to e. Once y is 1 to e, then log y is 0 to 1. That means it is 1 by y if y is in 1 from 1 to e and 0 otherwise. So this is the density function of that log y, e to the power x. Similarly, you can find the other case also. Now, what about if this is not a g is not a monotonic increasing or decreasing? Then what happens? Then we have to find that PDF of y is slightly in very also we should be very careful about that. So to find that PDF, we first find the distribution function of y. So take that this. So take y positive because if y negative, then it is 0 because y is x square, so x square cannot be negative. So for any y negative or is continuous type, so negative or greater than equal to less than equal to 0, that probability of y less than equal to y, this is 0. So now for y positive, so it is case 1, it is case 2. Then what? Then this is probability of x square less than or equal to y. Now when x square less than equal to y, that is what is the meaning of that? That means x is lies between minus y to y. Now what is this? This is probability of sorry, root y and root 1. Sorry. Now what is this? This is nothing but probability of x less than or equal to root y minus probability of x less than or equal to minus root y. So this is the standard normal distribution. And if you take that y is here, root y is here, and your minus root y is the symmetrical opposite point, then this area is actually the probability. This probability is that distribution function of that standard normal. So it is capital phi of root y. So it is the distribution function of. By the way, this remember that single point it is probability is 0. That's why we write it's less than or equal to. Then it is capital phi is the distribution function of standard normal distribution. And small phi is the standard notation. The small phi is the density function of the. So we should write a small phi. Is a standard notation for standard normal distribution. And now it is clear. So we just what is this? So 1 by root 2 pi e to the power minus y by 2 minus 1 by root 2 pi e to the power what? No, you just write it is what is this? This is you just put the 0 here. So this is this total area is nothing but 2 of the that area of capital phi root y minus half. Remember y is positive, root y is positive. So this that total area is just twice of that. Standard normal distribution is symmetric about 0, and that area is this part is half, less than 0 is half. So now we just take put that value. So this is twice of root 2 pi and minus y by 2 minus half. Sorry, oh no, sorry. This is not the oh this is not the PDF. This is a DF. So sorry. This is the small phi. We have capital phi. So first we have to take the derivative. Sorry. No, this is not the. This is capital phi is different. What is capital phi? Capital phi x is different thing. So it is integration from minus infinity to x 1 by root 2 pi e to the power minus x square by 2 dx. So that is a capital phi. So here's small phi. So you can't replace that capital phi into small phi. So you have to take the derivative. So derivative is that. So now the PDF of y is say h. So hy is actually the derivative of this dy of that probability of y less than or equal to y, and which is the derivative of this. And now what is the derivative of this? The derivative of this is twice derivative of the dy of phi y root y, dy of phi root y. So -1, so derivative of -1 is 0. Now what is this? So again you have to use a chain rule. So by chain rule, derivative of capital phi is small phi, the PDF of the standard normal distribution, and the derivative of root y is 1 by 2 root y. So what is so this is a root y. Now 2 to cancel out, 1 by root 2 pi, and 1 root y is also there, and e to the power minus y by 2, and 0 otherwise. If y less than 0, then it is 0. So hy is 0 if y negative. Sometimes we write in this notation, we write y in power of that, so y to the power minus half. So 2 to cancel out, this root y, 1 by root y is y to the minus half, that 1 by root 2 pi, and this e to the power minus x square by 2. X square is y is here, x is root y, so it is y. So this is nothing but the PDF of the chi-square distribution. So this y follows the chi-square 1. So basically this is the chi-square 1, and this is the PDF of the chi-square 1. The PDF of the chi-square 1 is 1 by root 2 pi e to the power y to the power minus half, and e to the power minus y by 2. Y, if y positive and if y negative, then it is 0. So what is that look? The PDF of the chi-square looks like this is 0 for negative value, then it's just picked somewhere, and then it's again is going to 0, asymptotically going to 0. So this is the PDF of this. So it is a h function, and this is the chi-square distribution and density function of the chi-square. So if it is not a strictly monotonic increasing or strictly monotonic decreasing, then we have to be very careful about that, and then we can't just cannot use that theorem. We have to go through the whole thing. We have to find the first distribution function and then take the derivative. So this is for today's lecture, and then next lecture we are going to the different moments and moment generating function, and then different generating function of random variable. There are different generating function of random variable, and then go into the expectation of that. So that's for today.